Dear students, today we shall be talking about general theory of relativity. For that, we need to begin with certain basic ideas like what is mass, what is weight, what is the true weight, what is the apparent weight, and then you also need to have an idea about accelerated frames of reference. So all of you know that mass is the quantity of matter contained in the body, and it is not to be confused with weight. Mass is just the quantity of matter contained in the body. All of you know that from your school level, from your elementary level. Now, weight is the force with which a body is attracted towards the center of Earth. With which a body is attracted towards the center of Earth. And we know that weight is a force. Now, if weight is the force with which we are attracted towards the center of Earth, then the first question that you may ask me as beginners that why are we therefore not drawn to the center of the Earth? Why are not we pulled? Why don't we get pulled to the center of Earth? Or in other words, why do we not fall through the floor? So why do we not fall through the floor is a very genuine question that follows. And the answer is that there are some contact forces, or call them balancing forces. They are kind of reactionary or restoring forces. Yes, these are the forces that counter this force, and the person who is standing on the earth, or the object that is standing on the earth, remains on the surface of earth and is not pulled towards the center. Now, what do I mean by contact forces or balancing forces? For example, consider a part of earth on which a man is standing, right? We know that the weight will be given by mg. It is the force with which it will be attracted towards the center of earth. But in response to this force, another force develops of its own, what we call contact force. And why do we call it a contact force? Because the feet of the person or the body of the person is in touch with the ground, right? So we call them contact forces or balancing forces or reactionary forces. You have learned that whenever we apply a force, a restoring force or a balancing force or an opposing force always gets created spontaneously. That is a law of nature. That is a very secretive law of nature, right? So same is the case here. You have a body with certain weight that is attracted towards the center of earth, but at the same time you have a contact force, a balancing force that is given by tension T, represented by tension T, and this T balances this mg. So this mg is the true weight, of the body. But this T is called the apparent weight. Apparent weight of the body. Remember that this topic, general theory of relativity, it begins from certain elementary basic ideas, but then it evolves into something very big, something very thought-provoking, right? So you have to gradually be with me to build this idea of general theory of relativity. I have indeed begun by talking about very small things like mass and weight, but have patience and try to build the idea. Now I'm talking about this tension, that this tension is the force which is opposing this mg, and remember, it is because of this apparent weight that we feel our weight. How do we feel our existence? How do we feel that we have a weight? When we walk, when we sit, when we are at rest, we feel that we have a weight. And how do we feel that? We feel that because of this reactionary contact balancing force called the tension, right? So remember that all weighing machines, they measure the weight of the body. This weight, apparent weight, right? They measure this T, tension. Now, when you are at rest on the surface of earth, when you are at rest, you are not doing anything, you are simply at rest, then the weighing machine is going to measure your true weight. because at that time this T is equal to mg. So the weighing machine will measure the true weight of the body. Now, the question arises when the body gets in motion. And in that case, we will take up a beautiful example, an example that is generally taken up when we make the students understand the general theory of relativity. And we take the example of an elevator, a lift that you call in the common language, a lift. Yes, this is an elevator or a lift in the common language. Now, many cases arise when this lift is at rest. And this is the person standing inside, right? Again, by the same condition, its true weight and apparent weight are same, and the weighing machine will measure its actual true weight. Suppose its weight is 84 kg. So the weighing machine will measure 84 kg. Now, if this elevator or this lift starts moving but with a constant velocity, since velocity is constant, again in that case, acceleration is zero. And we know that forces come into existence because of acceleration. When acceleration is not there, no force is there other than gravity. So again, the weighing machine will measure the true weight of the body. Again, I'm repeating that if the body inside the lift is at rest, the weighing machine will measure the true weight of the body. If this elevator starts moving but with a constant velocity, and since the velocity is constant, acceleration is zero. There is no additional force acting on the body. Therefore, this weighing machine will again measure the true weight of the body, that is 84 kg or whatever. But in case this lift or this elevator has an accelerated motion, then we are going to think. Now, remember that this tension always acts up, and we understand that the weight acts always down. Therefore, we will choose a convention that for all forces that act upwards, we will assign a positive sign, and all forces that act downwards, we will assign a negative sign. Therefore, when this lift or this elevator starts moving, it can either move up or it can move down. In case it moves up, we will assign a positive sign. In case it moves down, we will assign a negative sign. Now, suppose this elevator moves with an acceleration a. And in the first case, suppose it moves up. So what's going to happen? The upward force will be ma, mass into acceleration. Yes? And we know that the difference of these two, that is the tension which always acts up and mg which always acts down, will be equal to the resultant force ma. Yes, because for an observer that is on earth, standing here and watching the lift, for him, this man inside the lift is moving with the force ma. But that ma is the resultant of these two, t minus mg. We know that. And every person feels his weight, feels a force on himself because of this t. Yes? This t in a way acts through the body of the person. Therefore, it is because of this t component that a person feels his weight. He feels lighter or he feels heavier, right? So this t is equal to mg plus ma. So in this case, he is going to feel a bit heavier because this mg plus ma is obviously greater than mg, his true weight. So once the lift moves up with a certain acceleration a, the weight felt by the body for itself is greater than its true weight. In that case, the weighing machine is going to show us an extra reading. Say originally its weight was 84 kg, now it may show us 90 kg or something else. But of course, a value greater than 84. Now the second case arises when this lift moves down with the same acceleration a, it moves down. Now let us see what happens in that case. In that case, we know this equation t minus mg will be equal to minus ma. We have assigned a negative sign to the force because the lift is moving down. Therefore, this t is equal to mg minus a, which is obviously less than mg. So in this case, this person is going to feel lighter than usual. He's going to feel lighter, and the weighing machine will show us a reading less than 84 kg, less than the true weight. Say it shows us, say, 79 kg or something else. Now, another case arises that when this elevator or this lift has a free fall. By free fall, we mean when objects begin to fall towards the earth with only this much of acceleration due to gravity. This happens when you drop a certain object with a zero velocity. So you are dropping an object with a zero velocity, it falls towards the earth only with the acceleration due to gravity, and there is no other force. So in that case, what should happen ideally is that T minus mg is equal to minus mg, right? So obviously, because this lift at that time is going to have an acceleration g and it's moving down, it's fall, so it will be given a negative sign. This and this will cancel and T is equal to 0. So the person feels weightlessness. Remember, he feels weightlessness. And in that case, the weighing machine is surely going to give us a 0 reading. But remember, it is the feeling of weightlessness. The person, it's not that person is truly weightless. It's not that. And remember, see, this is the condition that on which you need to ponder upon for a minute because you are beginners in physics. So this is a condition in which the person feels that he is weightless, but actually he is not. And remember, most of the people feel that we will be weightless in absence of gravity. That is another condition. But this is a condition when, even if the gravitational force of Earth is present, try to understand this and try to remove all the confusions at the very onset of these concepts. That gravitational force or Earth's gravity is very much present. But because of a particular condition of the frame of reference, you are feeling this weightlessness. So, absence of gravity is not a necessary factor, is not always required, I mean to say, to feel weightless. If this condition is satisfied, you will feel weightless even in the presence of gravity. So this is true about astronauts as well, because a common question that beginners in physics ask, that why do astronauts float in space? Because they are also, in a way, caught in this condition. In the orbit around the Earth in their spaceship, the only force that acts on them is the Earth's gravity, that is mg, and it pulls them, tries to pull them down. And there is no other force. Yes, so this mg and mg cancels. Again, they feel weightless. T is 0. It is by the condition of free fall. They are also, so you should remember that these astronauts are also in a state of free fall. And that is why they feel weightless or they float. And the answer is not that they are moving in a gravity-free space. That's not true. 90% of Earth's gravitational influence is still there in that orbit. It's not because of absence of gravity. Again, I am emphasizing on it. It's not because of the absence of gravity, but it is because of fulfilling a certain condition of frame of reference, because of which a person or an object feels weightless at certain position, right? Now, I want to draw your attention towards another thing. So, by now I have cleared certain confusions like what is feeling weightless, what is free fall, what is feeling heavier, what is feeling lighter. But in all that, I actually talked about a frame of reference which moves with certain acceleration, right? So basically this gravity, as per Einstein, is not a force. We are going to build that idea. Is not a force, but it's an acceleration. But it is an acceleration. Yeah. Suppose you're standing on Earth. Again, we'll go back to a previous case. You are standing on Earth. This is the tension that acts through your body, vertically upwards, T. And this T is actually balancing this mg. And because of this T, you are feeling a weight of yourself. Yes? So this is a frame of reference which is associated with an acceleration g. Now, Einstein had an idea that if a person is moving in outer space, in a spaceship, which is moving up with an acceleration equal to g. Suppose this person has a mass m. What is the force that this person will experience? It will experience a force mg. Yes or no? Yes. And this is called the principle of equivalence. So, as per Einstein and as per common sense, it's true that the force experienced by a person in this frame of reference and in this frame of reference is same, that is mg. Here, the person is just standing on Earth. It is existing in the influence of the gravitational field of Earth. Because of that, it is feeling a weight mg. Yes? And here it is in the outer space, maybe in the gravity-free space, beyond the influence of the Earth's gravity, in a spaceship which is moving with an acceleration equal to g. So it will feel a force. This person inside will feel a force equal to mg. So ideally, these two conditions are same, and this is called the principle of equivalence. Now, we understand from the basic knowledge of physics that if two frames of reference are same, yes, then the results of an experiment should not change. That is, if we conduct an experiment in this frame of reference and if we conduct the same experiment in this frame of reference, the results should be identical. They should be same. Now let us choose a simple event, very simple event. And that simple event is a light signal. Light signal. So let us see what happens to this light signal as observed by an observer in this frame of reference and in this frame of reference. Now, since this frame of reference, that is the spaceship in the outer space, moving with an acceleration g, so suppose the light begins to start from this point, and because if this lift is moving, this spaceship is moving, this light will hit here, and then since it is advancing, then it will hit here, then here, then here. Yes, it is starting from the same point, but because the spaceship is moving, it is advancing with an acceleration equal to g. So what will the observer inside feel? He will feel as if the light bends, because light is hitting it at this place, then at this place, then here, then here. So for an observer, it appears to bend. So light is bending. Be very attentive, because we are building a good idea. So light is bending. Now, as per Einstein, if these two frames of references are identical, because they are carrying the same force, that is mg and mg, yes, they have the same acceleration g and g. Therefore, the results of an experiment or an event in this frame of reference and this frame of reference should ideally be the same. So what does he mean to say? He means to say that if we throw a light beam in this frame of reference, right? So a loaf is hitting at me at the moment I describe it to you. I know that I'll try my best to describe it to you. So if a light signal hits, so it should bend. It should bend. But remember, this frame of reference that we have idealized on Earth is not moving. So how should the light bend? Ideally, all of us expect that if this is the torch and this is the light that we have thrown, yes, it should hit straight. And light chooses the straight path, shortest path. But because of the principle of equivalence, this light has to bend. Now, this theory appears very, miraculous and philosophical. But in physics and in all sciences, remember, my students, you have to understand that no theory, no matter how much magical it appears to be, it cannot be treated as universal unless, remember, I'm setting a condition, unless it does not face the acts of the experiment. Acts of the experiment. Every theory has to confirm itself through some experiment, through some observations. Direct or indirect, it doesn't matter, direct or indirect. But it has to confirm itself by certain experiments. So Einstein was of the opinion that if the two frames of reference are identical, the results of an experiment should also be identical. So he expected that light should actually bend of its own. Yeah. So let us see what happened in confirmation to this theory. So on a full solar eclipse day, Einstein, together with his friend, observed that if a star was lying behind the sun, you have done an appropriate calculation and you have found the position of a star to be behind the sun. But the light reached the earth in this manner. Therefore, for any observer on earth who believes that light travels in a straight line, for him the apparent position of the star should be here. So this is the apparent position, but this is the true position. As per all calculations, all scientific details, the position of the star should be behind the sun, for example. But then why should the light reach us in this manner? For any observer who believes that light passes in a straight line, the apparent position of the star is here. But we know that actually it is here. By all calculations, by all confirmations, we know star is here. And this is not possible unless the light does not bend. So light bends. It confirms that light bends. And because sun is quite massive compared to earth, it is a heavy mass, it will lead to a greater curvature of this light. So this was the first direct experimental observation that light does bend in around the masses. It does bend. Another important observation was that, for example, if you choose sun again and the planetary system, the planet closest to sun is Mercury. Remember, this is the planet Mercury. Mercury never closes the orbit in which it moves. By that, I mean to say that this orbit also appears to move with respect to sun. It moves and it never closes a loop of itself. Yes? And this is again due to curvature of space-time. Remember, John Wheeler was a scientist, American scientist, physicist, who has summed up this general theory of relativity in a beautiful statement. He says that space-time tells matter how to move, and matter tells space-time how to bend or how to curve. Now, one more important thing that I want to address for my students is that why did I introduce this concept of time? Because by now we have been already only talking about space, and we have been talking about acceleration. We have not been talking about time. Remember, students, understand that for observing any event, any signal, any happening, time is important. Time is important. When you say that a ray of light has traveled from this position to this position, it has bent from this position to this position, it has taken some amount of time to undergo this. Remember, when you watch this video, what is this video? This video is actually a collection of so many pictures which are like beaded together in the form of a chain, yes, and that happens like these are so many pics, yeah, that are running, and we cannot be able to visualize it in the form of video unless there is not time. So at time 2 p.m. you were watching me writing something else on this paper. At time 2.5 p.m. you were watching me doing something else on this paper. So time is naturally associated with space, and space-time gives the complete fabric of cosmos in which you can describe an event. So all you have to remember is that this space-time, its curvature is determined by gravity, and gravity is not to be just understood as a force, but it is basically associated with an acceleration. And remember, all things in this universe are having an accelerated motion since the Big Bang, and it is more important to study the accelerated frames of reference, to study the signals, the events, the happenings in the accelerated frames of reference than the constantly moving frames of reference. So I think that gives you a basic idea of general theory of relativity. That's it.